All right, so we're going to get started with our presentation today. And we have with us Thayer Whitney with Dielectric, and he's going to talk about vertical polarization. We've had some discussions in the past during some of our presentations, but no real focus on this. I always find it fascinating, and Thayer, I don't know if you have all the examples of the applications that would be used with this technology, but feel free to give any and all examples.
Alrighty. Well, I will do the best that I can. uh, if I can find where the share screen button went. Alrighty. So, hello, my name is Thayer Whitney. As Mike said, I'm an RF engineer here at Dielectric, talking to you a little bit today about the importance of vertical polarization VPOL as it relates to ATSC 3.0. Now, before diving into the real sort of nitty-gritty of vertical polarization and all of that, I find it's sort of helpful to start from a slightly broader viewpoint of what does it actually mean to be ATSC 3.0 ready? Where does vertical polarization actually fit in to all of that? Also, just as a sort of an interesting bit and sort of help understand where we've been and kind of where we're going, what is the history behind vertical polarization. And then lastly, just how we at Dielectric are actually integrating vertical polarization into our products and how we deal with all of this. So when thinking about 3.0 and being ready for that, there is a couple of things that we need to bear in mind. So first is your peak to average power ratio being higher. We need to make sure that the area in the surrounding coverage area has a higher signal saturation. And that really goes sort of hand in hand with that next thing of circular polarization. So that combination of vertical polarization and horizontal polarization to make sure that we're able to provide service to these mobile devices that ATSC 3.0 has been really sort of targeting. So thinking about that, first thing, the higher peak to average power ratio, what is causing that? Well, it's really being caused by the modulation scheme that 3.0 uses. That modulation scheme, OFDM, you're probably familiar with it, orthogonal frequency division multiplexing. You have a number of subcarriers that are each orthogonal to each other. Because of their orthogonal, they are, in theory, won't collide or cause issue with each other, which means you can really push a lot more data across the airwaves than we were able to previously. Now, this is all great, but there is some things that we need to be cautious of and be aware of within this. So looking into sort of the time domain, it is a number of different frequencies, all in different phases. And most of the time under normal operation is fine. The interference and the combination of these signals don't really cause an issue for us, except when they do. And that is usually the case when a number of these subcarriers all align in their phase, which results in this much higher sort of peak in the power. And this peak in the power causes a higher voltage. The higher voltage can lead to dielectric breakdown, leads to arcing and our equipment getting burned, which we want to avoid. So moving on a little bit to that idea of signal saturation, what we're talking about here is really a sort of an ideal goal, sort of the holy grail, if you will, looking to get, for a proper reception of that bootstrap signal outdoors, ideally looking for about 48 dBu, and then sort of, the absolute, best case scenario, looking for about 95 dBu. And this gives us that full 25 megabit per second deep indoor to mobile small handheld receiver that is really sort of been, again, that sort of push that we've been looking for with ATSC 3.0 and providing service to these new sectors. So thinking about how you might actually accomplish this, sort of the first introduction of steering our beam here a little bit, you might think that, okay, well, perhaps the best way that we could do this is just simply tilt our beam down, and this has some level of success for about the first 4 miles away from your antenna. The downside is it really only works about that first 4 miles away from the antenna before your performance is pretty seriously degraded. Better idea, a more prudent plan, is something called null fill. So taking a little bit of power away from that main beam of the antenna and sort of pushing it a little bit lower in the elevation pattern. And as we can see, this gives us that similar level of performance jump, but without the complete and utter degradation at the far reaches. And so when contemplating these two options, it's generally advised to stick with that sort of null fill. Downside is, for no matter how you go about accomplishing this, is your total range is going to be decreased, which means you have a smaller area of coverage. And the solution to this is add some form of SFN or single frequency network to fill in that gap around the outside. So moving on a little bit to the history surrounding all of this. And if we look back, early 1900s, 1910s, we see that the broadcast industry is really just focused on using horizontal polarization. And as time goes on and people experiment with holding our dipoles in various different directions, it's realized that different combinations or different types of polarizations have a better effect depending on the scenario that you're in. And so by 1946, we see the FCC authorizes the supplemental use of vertical polarization for FM broadcasts. Now, a few years later, the unit head of development at RCA, Dr. Matti Sukla, starts developing a single element dual polarized antenna. And this is really the first of its design, and it's the BFC line. And this design is extremely successful to the point that ring style antennas are, even till this day, still sort of modeled after them. Looking forward a little bit, seeing the success with FM and its vertical polarization integration, we see the FCC authorizes the use of circular polarization for TV stations. And at this point, most TV stations are going to start using a combination of horizontal and vertical polarized interlacing for their elements. But RCA, busy at work, going through, starts developing the TDM and TCL, which are both dual mode polarized single element antennas, and see great success in this area. And it's so great, in fact, that RCA is actually awarded an Emmy for their work in circular polarization. Sadly, this is the end of an era for RCA, as in 1986, their division for broadcast is shut down. But not the end of the story, as the IP and the engineers, or at least some of them, are picked up by Dielectric, and they sort of continue that journey forward. And just a few short months, year or so later, we see the Dielectric developed concept of a parasitically fed dipole, which, similar to the ring antenna, has been extremely successful and has continued to be used with great success even till today, and its sort of variation and descendants. Up through the late 80s and the 90s, we are seeing circular polarization have really solid impact in both the VHF as well as the UHF spectrums. And this is really due to the fact that at this point in time, we're still using analog broadcasts, and you have the issues of multipath fading, which causes that ghosting on our screens. And this helps alleviate some of that. Now, as you get into the end of the 90s and the early aughts, we're looking forward to a digital transmission age. And the ATSC finds that circular polarization adds no benefit to stationary DTV services. Now, if by this point I have not completely put you to sleep, you might be kind of wondering, what? You're here to talk about vertical polarization, and you're telling me that the ATSC even 20 years ago was finding that it has no benefit. Well, kind of, sort of, no, yes. The idea here is that ATSC 3.0 is really trying to focus on not just the stationary customer, but we're really trying to focus on is, yes, continuing to provide service to the stationary customer, but we really want to make sure that we're getting access to the mobile customer. So at this time, with this sort of pushback coming, Dielectric decides to try to put this all to bed and begins doing a fair amount of testing. And starting out first in our lab in the anechoic chamber, set up on the transmission side, both circular transmission as well as vertical and horizontal transmission. The environment is set up to be a very heavy scattering environment. And at the other end, we have a simulated handheld device that is sitting there and turning on a turntable. And the point of this testing is we want to make sure that we're measuring the received signal power versus the antenna orientation and its location as it's going through, carefully calculating out the mean of that data, which presents the signal level that that system was designed for, and then looking at that variability spread between the mean of the signal and the desired probability service line. And this variability spread, looking at about 2 standard deviations, anything that is giving us an improvement in that SN margin is really what we're looking for here. Because as that goes up, your reliability goes up. And so what we find is that measured in this very heavy scattered environment, for the horizontal polarization, we have about 19 dB, and for vertical polarization, about 20 dB. But for the circular polarization, we're looking at about 15 dB. So looking at about 4 to 5 dB improvement in that signal variability. And as we finished, kind of publishing these results and talking about this a little bit more, there was some pushback. Because at this time, again, we're looking forward to a digital area. And the pushback was, well, you're just looking at the signal to noise ratio. That's not applicable. We don't care about that anymore. We care about bit error rate. Okay. Well, first, bit error rate and SNR are inversely related. As your SNR improves, your bit error rate goes down. And so, especially in this region, we're looking at a margin of improvement between each of these two SNRs. So for about 5 dB improvement in that margin, we're looking at dropping our bit error rate from about 10% down to about 0.1%. And so this margin of improvement is really what is contributing to the improved reliability in this service. Again, targeting these mobile devices. But fine. Putting all this aside, we'll go out and we'll actually test this in the field. And so this device here, this is Ralph. He is our rotational advancing linearly polarized handheld. Pretty happy-go-lucky individual, happy to get pushed all over the place, and took him down to Tampa to do a bit of testing down there. And so you can see here, upper right corner there, one of our technicians pushing him along there in his parallel configuration, dipulse in there spinning perpendicular parallel to the ground. And then looking down, you can see in some of the other examples, the perpendicular. So testing these two, to see what sort of coverage we're actually getting here. And so wandering all over the Tampa and tested them in a whole bunch of different areas, including, driving and that sort of thing. But really today, just sort of talking about the outdoor and the indoor testing that we saw. So first up, we looking at an outdoor wide open area, about 4.2 miles away from the transmit antenna. And, we got a pretty good result. We're pretty happy with this. So for the parallel dipole, looking at about a 13 dB improvement in that margin. And then for the perpendicular dipole, looking at about a 5.5 dB improvement for that margin. This next one, looking in a outdoor residential area, about 15.2 miles away from the transmitter, a bit of a harder scenario. There is a number of trees, you have houses, so there is some fading that's going on here, a little bit of scattering, but not too terrible, especially compared to other things that we'll talk about in a minute. And we see here that, again, getting pretty good improvement in reception. So looking at about 11.5 dB improvement in the parallel and about a 5.5 margin improvement for the perpendicular. So last example here, talking about a indoor mall. And this is sort of real worst case scenario. Large industrial building, lots of metal, lots of reflecting surfaces, really kind of makes it pretty rough on our receive antenna here. Very, very heavy small scale fading. And this is about 8.7 miles away from the antenna. And we see that the parallel, kind of as expected, there's just a bit of an improvement, but as compared to the perpendicular, we're getting a large improvement, which is good sign. And the kind of the takeaway from all of this is that for all of these tests that we've done, from your controlled environments out in the lab with the anechoic chambers to these field tests, it all is pointing to the fact that, you know, circular polarization is it just leads to a 5 to 7 dB improvement in reception. So how do we actually deal with this? How do we actually implement this? Looking back to the 60s, the vertical polarization, horizontal polarization combination was done with, one half of your antenna being vertical, the other half of it being horizontal. And this, had some downsides to it. First, each of these antennas are spaced out about a wavelength apart. So for each layer, you're, especially in the low and the mid band, your antenna is going to get pretty high. But more importantly than that, you have two main beams that are coming off of this, your horizontal and your vertical, and there's only one spot, basically just directly straight out, where the axial ratio or the reception difference between the horizontal and the vertical is the same. And so we see the start of really the first interlace designs here, alternating between that vertical and your horizontal polarization. And this is a really big improvement over what you previously had. But you still have the problem that each of these is going to have a different wavefront, which means that each of them is going to have only one spot where they are actually achieving a circular polarization. And you have more of these because you have more of these sort of layer combinations, but it's still not ideal. And this is even addressed back in the 60s in this paper from Thayer. Fast forward a bit to the advent of vertical polarization getting integrated with TV stations for the circular polarization. And unfortunately, physics didn't just magically change. Interlace designs are still causing you a bit of a problem here. And this is especially true when you're looking, you take about 6 degrees of depression off of that main beam with an interlace design, and you'll actually find that there is about a 19-degree phase difference between your horizontal and your vertical components. Now, what that means is that you have about a 3 dB difference in your axial ratio. So again, that ratio between the receive power of your vertical and your horizontal. And not ideal, but certain designers still are okay with that and they'll accept that. But by the time as you continue down, by the time you hit 30 degrees, you're at a full 90-degree phase difference. And your axial ratio is at infinity. which just means, you're only receiving one or the other. You're not receiving both. And, to make matters worse, especially now with some of the new FCC's regulations, because of this change in the phase, you actually end up with a complete change in your polarization. So you go from right hand, which is what's required, to left hand polarization. So minor deals, just violating FCC regulations. Now, looking at this, you might be kind of telling where I'm going with this, which is when you look at parasitic dipoles, that problem is sorted because you have both elements that are tightly coupled together, and your axial ratio is kept constant through all wrangles of depression, which means that you don't have any spots where you're violating the FCC regulations, and your users are actually going to have a better experience overall. Kind of putting this into a more practical example, you can imagine walking towards an antenna that has this interlaced design. You're passing constantly through the different these different axial ratio combinations, which means that for someone who is holding a handheld that is probably does not have the best antenna inside of it, that reception is going to be all over the place. Worst case scenario, you're looking and you're holding your phone and you turn it to go full screen and you just completely drop the signal and you lose your feed. Now, this is, if you think back to the history slide previously, you might be thinking, well, perfect, this is back in the 80s, solution has been solved, or the problem has been solved. And unfortunately, no, it is not. For us, at least it has. We always use these parasitically fed dipoles, but there is some inferior designs that float around that continue to use that sort of interlace fed vertical polarization. So to wrap this up, because I am starting to push on to that half-hour mark here, I'd like to wrap up here a little bit by talking about, how have we at Dielectric tackled, some of those other technical challenges that I mentioned earlier. And so every antenna that we have shipped since repack has come with a feature that we call future fill. And future fill is a feature that allows us to, with very, very little downtime or very, very little interruption to service, allows us to take from that, that 1.0 pattern to a new 3.0 pattern with that, that higher melt fill. And, the way we do that is we try to keep it as simple and as elegant as possible. You have to have a rigger climb up. If it's a panel antenna, you flip a couple of the panels around. If it's a slotted coaxial antenna, change a couple of couplers around. And this is really beneficial to you because it is, very small amount of downtime. You're looking, especially for a slotted coaxial, a similar amount of time to have somebody go up is to change a light bulb up there. And also too, there's no complicated, sort of Rube Goldberg contraption that gets bolted onto this thing, in the middle of the air. So your VSWR, all of these characteristics, they remain exactly the same. And so once they're up, they switch it and you're back on the air. So talking a little bit too about, you sort of mentioned SFNs and sort of the things that go along with that. There's a couple of things you can think about for us, kind of the workhorse that we are typically thrown out of here are the slotted coaxials. These are great. They're pretty low wind load and they have really, really high variability in their pattern. Pretty much whatever you would like. Downside being is that they have a limit to their channel range. If you need something that has a real high front to back ratio, we produce a couple of these cavity back radiators, and these are also fantastic. Again, real high front to back ratio, and they're also particularly well suited for wideband situations. So it just depends on the application and what you're looking to achieve. So thank you for inviting me to come talk to you guys. I've really appreciated it. And if you have any questions, I will do my best to answer them.
All right, floor is open.
I have a question. I'm not sure if I'm even asking the right in the right way, but the future fill, does that mean the drawing showed doing one section of it? Does that one section, are you doing the whole thing like that?
It is not the whole thing. It is, it depends on the antenna, it depends on how many layers you have, but it's just a couple of the sections that you'll have to change over.
Okay. So that's all it needs, really, I guess.
Yes.
Interesting.
Hey, so you gave Tampa as an example test market, and there was a station. How many people are doing this right now, experimenting and maybe even tweaking the polarization?
At this point in time, so I mean, this testing is something that we did a while ago, really, and it got to the point where, between what we saw with that and between what we see in simulation now, because as much as I would love to go play in an anechoic chamber, what I can do in an anechoic chamber, I can do in a day, I can do in 20 minutes in HFSS. So at this point, I don't know that there is a huge amount of continuing experimentation of sort of trying to prove that it's worthwhile. Each environment that you're deploying your antenna into, it is, it may not be the right choice to be fully circularized. You might want a bit more of a split between your H-pole and your V-pole. It just depends on, are you in a farm field out in Iowa, or are you in, New York City?
Got it. Any other questions? Fascinating topic to me. And you did a great job explaining it. Thank you.
I'm glad I was coherent.
Yep. All right. If there aren't any other questions, we will.
Yeah, I got a quick question. How can you tell if it's a coaxial antenna or a panel from your model numbers?
That is an excellent question. From the model numbers, are you talking about being on our website and looking around?
Yeah, like we got a quote for a TFU ETT, which looks coaxial to me, but
from the numbers that you are provided, you can go on and you can look, and they are usually, they will say within the data sheets what type of antenna they are.
yeah.
If you have any questions, I would really encourage asking our customer support. They're always available pretty much. So
all right, so at this point, you're recommending a panel antenna
for
like ATSC 3?
It would really depend on what your need is.
Okay.
It depends on the frequency ranges. We do a fair amount of slotted coaxial, pylon style antennas. Panel antennas are an option for you if you need sort of a very wide frequency spectrum. Nowadays, we typically suggest our WB line, which is a cavity backed radiator, similar-ish performance to a panel antenna, but not quite as wideband. But it covers most of the TV spectrum. So again, it just really depends on what your use case is, what channels you have out of your station, etc.
Okay. All right. Thank you.
Yeah, absolutely. Got anything else for me?
Oh, will the slide deck be available?
Yes, I am intending to re-record this later today with a bit better quality than the mic that's on my desk. And I should make that available to Mike here shortly.
All right, great.
Yeah.
Thanks.
And we're recording it and we'll post it to our YouTube site. It'll be the chapter 60 site. Chapter 54 is welcome to do the same.
Thayer, just a quick, you may have covered this, but is there much difference in bandwidth between ATSC 1 and 3 that would require a new antenna for many stations?
I don't think so. your low band can be a bit difficult because, you have a very low frequency that you're trying to couple to, ideally with your iPhone. If, as long as, you have bought an antenna, specifically from us, if it's been bought since repack, it has that future fill option and it can be converted very easily. It really would just depend. Again, there's a sort of hate it to say, well, it depends, but it really does depend. It depends on your scenario. Quite probably no. The only thing that you might need to look at adding is those additional single frequency networks. So, as your footprint is sort of pulling that power in closer to the antenna to boost that signal strength, just by that nature, you're gonna be tucking that edge back in a little bit. And so in any of those areas that are low receiving in power, you're going to need an additional sort of supplemental tower to fill that in.
Thank you. Appreciate that.
Yeah, absolutely.
Any other questions? All right, Thayer, I hope we get to see you in the future. Come up with something else.
Absolutely.
Talk about.
And if you think of any other questions that you'd like to ask me, you can reach me at my email. I do my best to try to answer those in a coherent sense.